Welcome to the next video, everybody. Today is going to be all about Hopf algebras. So what's the setup? The setup is we're going to specialize the discussion from the previous few videos to the category of schemes over S, written sk over S. An S group scheme or an S group is just a group object in the category of schemes over S, okay? And then GR over S or GR over S will be the category of S group schemes for us. That's kind of its own category within sk over S. And typically the base scheme S here will be affine, so like S equals spec R for some ring R. And as usual in algebraic geometry, when I want to write things like sk over spec R, I'll just write sk over R. And instead of saying spec R group scheme, which is the proper way of saying things, I'll just say R group scheme and we'll all know what I mean. Okay, reversing the arrows. So let's let G equals spec A be an affine R scheme. We know the category of commutative R algebras is contravariantly equivalent to the category of affine R schemes. This is a basic fact from kind of introductory scheme theory. And so what that means essentially is that making G into an R group scheme is the same thing as giving R algebra homomorphisms M tilde from A to A tensor A over R, epsilon tilde from A to R, and inf tilde from A to A. Essentially because like spec of a tensor product here is the product of the specs, right? So when you apply this equivalence of categories, tensor products go to products contravariantly. That's kind of where all this comes from. And these maps correspond to the morphisms and epsilon and inf discussed in previous videos. And of course, these new morphisms have to commute the diagrams you obtain from the associativity, unity, and inverse axiom diagrams just by reversing the arrows, replacing S by R, G by A, cross by tensor over R, putting tilde on all the arrow names, and then just kind of recognizing what delta tilde is. Delta was the diagonal map. So what should delta tilde be? Well, it should be induced by the multiplication in A. It should be a map from A tensor A over R to A induced by multiplication. Okay, these maps have names. M tilde is called the co-multiplication. Epsilon tilde is called the augmentation or the co-unit. I think most people probably call it the co-unit. And inf tilde is called the antipode. Okay, so what is a Hopf algebra? It's just a commutative R algebra A equipped with these three maps. Okay, it's very simple. The category of affine R group schemes then, by this discussion, is contravariantly equivalent to the category of commutative Hopf R algebras. Of course, I have to tell you in that category what the morphisms are. They're homomorphisms of Hopf algebras, which is unhelpful. What are those? Those are homomorphisms of R algebras regarded as bi-algebras. What does that mean? A homomorphism of Hopf R algebras, finally, phi from A to A prime, let's say, is a homomorphism of rings such that the following four diagrams commute. Of course, you want the structure diagram to commute with the two R algebra maps. You also want kind of the reverse of that diagram to commute because kind of the reverse of these arrows is the epsilon tilde arrows. So you want that to commute. But you also sort of want the delta tilde and the M tilde squares to commute. So you have one square here, which has the delta tildes as the left and right maps. And it has the tensor product as the bottom map. And then you can reverse arrows, but the reversing of the arrow of delta tilde is the M tilde map. So the four kind of obvious diagrams you want to commute have to commute for this map to be considered a homomorphism of commutative Hopf R algebras, I guess, if you like. Okay, just a couple more things. Let's let G equals spec A be an affine R group scheme. The kernel of the co-unit epsilon tilde is an ideal I equals I sub G. It's usually just called I inside A, and it's called the augmentation ideal because it's the kernel of the augmentation map. It's a very important thing that we'll use to do quite a bit. So you just want to kind of keep that terminology in mind. And as R modules, we have A equals R times 1 direct sum I, essentially just because the canonical map R to A is a section for the map A to R, right? And so this exact sequence 0 to I to A to R splits. So that exactly gives you this. And this isn't hard to check, okay? And hence, for example, like if I wanted to do A tensor A, another way of calculating that would just be to do R direct sum I tensor 1 direct sum 1 tensor I direct sum I tensor I, just by using basic properties of direct sums and tensor products. And then lastly, I want to give you an important property of co-multiplication. We'll use this a couple times. Turns out that if F is an I, the augmentation ideal, then M tilde of F minus F tensor 1 minus 1 tensor F is actually an I tensor I. And that's easy to check. You can apply epsilon tilde tensor the identity, and then identity tensor epsilon tilde, whose kernels are, of course, I tensor A and A tensor I, respectively. You can check that those kernels have intersection I tensor I, although that's obvious. And then you apply these maps to elements of that form. Okay, so you're all set. This kind of just pops out easily. This is an easy check. So next time we will finally actually start looking at examples of group schemes. And so I will see you then. That'll be next week. So thanks for watching.